Hello and welcome. Thank you for spending time with us today for part 3 of our Instant Insight series on elastomers and rubber compounds. My name is Troy Nickel and I'll be your host today. Our speaker today is Sadegh Bedad, who's an applications engineer here at TA Instruments. Sadegh has a PhD in material science and did a bachelor's and master's degree in polymer engineering. Prior to joining TA, Sadegh worked as a senior material scientist at Magic Leap. There he supported material design and development teams on selection of material candidates and where he did testing various materials and components for virtual reality goggles. After Sadegh presents, I will relay any questions you submit via the Q&A tool available in the lower left of your screen. So please feel free to send them in at any time during the seminar and I'll relay them at the end. There's also resources available in the lower right, accessible with the folder icon. So Sadegh, thank you for presenting today. I'll now hand it over to you.
Hi everyone. Thanks Troy for that introduction. So today we are gonna talk about how we can correlate cured rubber characteristics to the product performance. This is part 3 of a 3-part webinar that the first 2 parts were done by my colleagues Sarah Kotz and uh, Dr. Alina Latshaw yesterday and the day before. And if you missed those, I encourage you to watch all of those in the archives. So with that introduction, uh, we'll start with the outline of my webinar today. We all know that when your rubber product is made, there are a couple of generic tests that everybody does. You look at its hardness, you look at its density, you'll look at compression set, tensile rebound, things like that. Uh, but we have all encountered situations where we have 2 samples that give the same numbers on those tests, but when it comes to the actual performance when the rubber meets the road, they behave different. So the goal of this talk is to show you what are some of the better ways that you can compare these different formulations, different processing techniques, different raw materials to ensure that in the end your customers are satisfied with the product that delivered to them. We will discuss a couple of internal studies that we did to show you how post-cure and aging can be characterized by the DMA instrument. We'll talk a little bit about how the environment and exposure can change the properties, and we'll also talk about electroforce load frames and doing heat buildup tests and fatigue tests. And in the end, I'll mention a few other techniques such as thermal conductivity or tribology and dielectric measurements and TMA. So when you think of your rubber product, you start with a selection of raw polymers, right? You have a certain type of polymer and then it has a molecular weight and molecular weight distribution. Then you add some fillers and additives to it. They can have different loading percentages. Uh, they can have different shapes, different surface treatments. Then there are various ways you can introduce these into the rubber and either mold them or extrude them, play with your cure time. And in the end, you get a molded or extruded part. And what matters most is that do you get the viscoelastic properties that you were looking for or you didn't? So if we look at the steps of this process, yesterday and the day before, we focused more on earlier stages of the process where you are still working on a material that is in the liquid or semi-solid uh, state. But today we are gonna focus on the lower right corner. When you have the actual piece of rubber in your hand, uh, and then how you would measure its properties. First step, like we talked, is measuring the density and hardness. Uh, TA, we have two automated machines that can do automated density measurement and automated hardness testing. Typically, the samples for density measurements are uh, 30 to 45 millimeters in diameter. You can load up 20 to 30 samples. Our automated density tester operates based on finite difference method. So it relies on measuring the weight of the sample dry and then immersed in a fluid, usually water, and you would correct the density of the water for temperature to have very accurate measurements, and then you get to choose to dip it a few times to make sure that it's fully wet before you take these measurements, and then you compare the weight of the rubber piece inside water and in air, and this way you can measure the volume of the specimen with a high accuracy irrespective of its geometry. So that's how you would measure the density. And then for hardness, uh, you can look uh, look at like shore A hardness. We have a rotating mechanism that will ensure that you rotate the sample and take several measurements on a single specimen so that you know that the measurements are representative of that sample. And then the software will automatically store all those values and report the mean and median for each specimen. So this way you can set pass-fail criteria for your samples, and the software will do the analysis for you. So going to more advanced techniques, the next type of test that you can do on your rubber would be typically a DMA test, or a dynamic mechanical analysis. And what that means is that you are basically measuring your material response to a cyclic deformation most of the time. And that helps you measure your viscoelastic properties, such as storage modulus, loss modulus, and the phase difference between the deformation and the stress, which is called tan delta. So some of the common uses of this technique would be identifying a glass transition with better sensitivity. Because of this applied mechanical stress or deformation, this technique usually have a better sensitivity to EG measurements compared to DSC. Uh, about 100 times to 1,000 times more sensitive. It's very good in detecting secondary thermal transitions such as beta peak that may not show up in a DSC graph. We have two different types of DMAs shown in this slide. The one on the upper right corner is a DMA 850. Many of you are familiar with that. It's the best-selling DMA in the world. It's very good in doing a lot of various tests, not just doing the typical DMA test. For example, you can measure shrinkage forces and length changes. With that, you can do tensile testing. And then in the bottom right, you're looking at another version. In cases that you need higher forces above 18 newtons, or you have other needs such as fatigue testing that you can't necessarily do with the DMA 850, you would go bigger and you would use a higher force DMA. We call that a DMA 3200. So we'll show you some example studies that were done with these two machines and discuss the slides with you. Comparing RPA and DMA, like I said, most of the time when you're dealing with earlier stages of the process, you're still focused on the process. Your materials is still semi-solid or just cured in situ. In the RPA, you would use an RPA. If your material is mostly solid, fully cured, that's where you would go to a DMA machine. And your material can have various shapes and sizes, unlike RPA. So that gives you the ability to test, for example, field retrieved materials or molded parts that cannot be done on an RPA machine. Um, so today, as we go through the slides, you'll see four little icons in upper right corner of each slide. What I mean by those is that we are trying to categorize the type of test that we are doing on that sample. So we are looking at, are we measuring form release and cool, or are we measuring the material response under loading, or are we looking at post-cure and aging or exposure of your material to things like chemicals, moisture, or thermal changes. Uh, First example that we are going to discuss today is a rubber conveyor belt. So this test was done on a DMA 3200, which has 500 Newton force capacity with a large sample of it. I think this is a very good example to show you why you would need a high force DMA. This was a layered rubber composite. You can see the woven parts near the bottom of the sample. The sample was rather big, so 200 millimeters long and 24 millimeters thick and 25 millimeters wide. And if we were to cut this sample, and they tried, you can see that on the left, uh, the results won't be representative of your composite. That happens in a lot of cases where the size of the cell is such that your stiffness is going to be really high. And that would push you to high force DMA. So that's why we switched from DMA 850 and thought DMA 3200 is a better choice in this case. So this rubber composite is used on a conveyor belt, and in that application, they wanted to know the changes of the viscoelastic properties with temperature. So in the left, you can see a picture of the sample on a three-point bend clamp inside the oven, and you can see that the span is really large. So it's a 100 millimeter span. We did this test at 10 hertz and 1% oscillation strength. And you can see that the glass transition temperature can be marked by three different methods. So by the onset of that drop on the storage modules, so that's the blue curve. You can see that we measured minus 37 degrees for gas transition temperature that way, or you can look at the maximums of loss modules, which showed us minus 33 degrees, and then lastly, you can look at the peak of tan delta, which showed us minus 24 degrees. Any of these three can be used, and in the standards, you see that all those are brought up. The main thing is to realize that there is going to be some differences between the TGs that are measured with each method, and when you're comparing materials, stick to the same criteria that you used in your previous experiment. So it's not a good practice to compare the TG that is measured by, say, onset of the drop in storage modules with the peak of tan delta. Most people prefer peak of tan delta because that's the easiest. So this graph shows you uh, exactly why we tried this test on a DMA 3200 uh, machine. Uh, you can see that if you were to do 1% oscillation strain, you can, uh, this is a strain sweep that is shown on the left, on the right, sorry. And we are looking at maximum and minimum of that oscillating waveform on your sample and how much load is exerted on your sample during that as you go to higher strains from the left to the right. So this is a compression test. That's why the values are negative and everything is below zero. At around 1%, because this was a log scale, so the test measurements are spaced so that they're evenly distributed along a log axis. That's why it's not exactly 1% here. You can see that the forces are changing, so it's oscillating between minus 30 newtons to minus 153 newtons. And in the end, as we get closer to 1.8%, we are looking at something around minus 56 newtons and minus 277 newtons almost. Bear in mind that in this specific case, we picked that value for the span uh, because because of the restriction that I had, because some of the sample was cut. The fixture allows you to do bigger spans if you wanted to. In fact, there are some shear studies and shear type tests that are done in composites space that need very short spans, so that you measure, you create a lot of shear in the neutral plane, and you could do those, or you could go with bigger spans if you wanted to. So this is an adjustable 3-point bend clamp. Um, then going to the next example, uh, we are going to discuss effect of aging on your sample. In this case, we had an elastomer O-ring, and we measured its property when it was new and after it was aged. Why is this important? Because a lot of time when you replace an O-ring in a device or an instrument, you would want to make sure that it has the modulus that you're looking for. So what you can see here is that with time, the modulus is increased and your peak of tan delta shifts towards the right. So in a sense, it seems that aging is improving your properties. Uh, why is that? Because the curing is still progressing in your sample when it's new. And as it goes on, you can see that uh, you create more cross-linking points. So that shifts your TG to a higher temperature and your modulus to a higher value. You can see that both storage modulus and loss modulus are almost doubled in the age sample. So here's another graph showing the same thing on that sample. So here, instead of sweeping through temperatures, we are sweeping through frequencies from 0.1 hertz to 10 hertz. And we are looking at the changes in moduli in the age sample and compare it to the new sample. And you can see that your modulus increases, is almost tripled in loss modulus, and in a storage modulus is almost double. So again, why this is happening is mostly because of cross-linking. If you have a network of polymer chains and you are looking at molecular weight between cross-linking points, shown by those two red dots in the schematic that you see here, as the molecular weight between the cross-link points are decreased, meaning that that length is reduced, you will have a lower molecular mobility. So you're creating a network that restricts chain movement. And that restriction in chain movement and reduce the free volume will increase the TG of your material. If you were looking at just an unfilled polymer, here's the equation that can show you how that change is gonna be. So you would look at your storage modulus in the rubbery state, and by changing your cross-link density, you are gonna create lower and lower M sub C's, and that will give you a higher modulus at room temperature. Here's another example. In this case, we are looking at highest styrene SSBR. In this case, we are looking at highest styrene SSBRs. In a lot of cases, you're adding highest styrene level because you want to increase the stiffness of the thread compound to enhance some properties, for example, high speed handling. Or in cases when you have a functionalized SSBR, you know that the stiffness is gonna change because you are manipulating the polymer filler interaction. So here we are trying to understand when we go with formulation A to formulation B and then the third formulation, which is a functionalized SSBR, how that changes your material performance. A typical example is doing a temperature sweep, looking at how the TG changes and looking at your tan delta values at 0 degrees C and 60 degrees C. So the literature on DMA testing shows that increasing tan delta at 0 C it is going to improve your wet traction. So that helps you not skid on the road. Conversely, lowering tan delta at 60 C is going to give you improved rolling resistance. So you're reducing friction and improving your MPG. But most of the time, it's a trade-off. In simple compounding methods, you either increase both or reduce both. So it's important that when you are trying more sophisticated formulations and optimizing both of these, trying to increase the wet grip and also reduce the rolling resistance, to do this type of test, these temperature sweeps can tell you if you're going in the right direction. In this example, we can see that when we went from formulation 1 to formulation 2, we improved the wet grip and the rolling resistance didn't change much. So if we were to pick between these three, considering that almost equal rolling resistance is shown, it seems that when you functionalize your SSBR, you reduce the rolling resistance and then also improves the wet grip indicator. So that sort of would be the balance if you're looking at both of those. That would be your optimum formulation in this case. So the next example will be showing you the effect of exposure of your rubber to a plasticizing agent. So this is really interesting because we are looking at EPDM rubber. We all know that EPDM has a better temperature resistance and That's why it's used in many applications over natural rubber. Um, in this case, we had two EPDM samples, and DMA 850 allows you to measure viscoelastic properties when the sample is submerged in a fluid. In this case, we tried a vegetable oil, and the, you can see that after the sample was soaked in oil, the TG was reduced by 7 degrees, and you had 30% drop in modulus at room temperature. So the reason for that is that the oil molecules are diffusing into your polymer, and they're acting as a plasticizer. So that increases chain mobility, and that's why your TG shifts to lower temperatures and your modulus drops. In the next example, we are going to look at the effect of both loading and different environmental conditions. So this is a test that is done according to an ASTM test method, ASTM D623, or also known as BF Goodrich flexometer test. We are just doing it with our instrument, which allows you better control of load and deformation, and also collection of viscoelastic data rather than looking at, I would say, even simplistic measures such as just the residual strain on your sample before and after. So the goal of this study was to compare some suppliers of BR rubber, and a comparison also between two different mixing methods. So one was the conventional mixing of master batches, adding fillers to master batches first, and then mixing everything in bamboris together. And the other was a phase mixing method. We'll describe it a little bit more in the next few slides. And then we are going to look at the heat buildup or the blowout performance comparison. The mean stress that was applied to the samples was around 2 megapascals. As you can see, this is a very high strain test. In a lot of DMA tests, you would test your samples in linear viscoelastic region, but in the actual application, a lot of times the rubber is not used inside LVR. So using an electroforce machine allows you to push it further to what is actually representative of the actual surface of that rubber compound. So this test is trying to replicate the strains that the sidewall of a flat tire experiences when you're still running on it, and to show how long it takes before that rubber sample completely fails. The standard sample size is 20 millimeters tall and 17 millimeters in diameter. In this case, our samples were molded differently, so this was a 20 millimeter by 20 millimeter. It's a compound that is made of 70% natural rubber and 30% butadiene rubber. So this is a typical tire formulation, and all of these samples were formulated such that they show the same hardness and Mooney viscosity before they are cured. So we are trying to show that those measures may not be enough here. You have a pair of insulated platens, as you can see on the left here, that trap the heat that is generated due to this oscillation that is on your sample. So those are phenolic platens, and there is a thermocouple that is touching the base of that rubber cylinder. So we are also monitoring the temperature increase with time while inducing a significant amount of deformation on the sample. The test is done inside an oven because you want to make sure that you're controlling the ambient temperature really well. Usually you do tests at room temperature, 50 C and 100 C to get a perfect feel of how different your samples behave. Now, my colleague Tim is going to show you a short video just to give you a sense of how this is done and how high these strains are. This is a slow motion video. The test is actually done really fast at 30 hertz. And if he can replay that video for you one more time. You can see how highly compressed that sample is. The oscillation strain was only 12.7%, but the test dictates a mean force or a mean stress to be applied to your sample before you start oscillating around that. And that alone is gonna add an additional 30 to 35% strain to your sample. So it's a very aggressive test, and we are going to compare the results of 3 different specimens. So we are testing 2 of each, and what we are looking at here, we are looking at the temperature increase with time for these 3 formulations. So each color represents a different supplier. You can see that the ballpark temperature rise for all of these samples were about the same, slightly higher for a solid sample. But what is interesting is that the Comha sample, it failed at around 40 minutes. The Cyber Rosland sample, it lasts longer. It failed at around 45 to 50 minutes. But the Brasali samples didn't fail. So that tells you that that's probably a better raw material in this case. And here are some pictures of the samples before and after the test. So the standard says let the sample sit at room temperature for an hour, and after it's relaxed for an hour, measure its height and compare it to what it was before running the test. So looking at these samples, you can see that there are going to be some ruptures in the material as the rubber bonds break, and some gases are created due to the breakage of those bonds and chain rupture. Those gases are trying to get out, and in tandem with the stress that you're applying, that breaks the external wall of the cylinder, and that's why it's called a blowout test. So here we are looking at where we started and how the samples that failed look like. So going to the next slide, here is where we are comparing different mixing methods. Let me elaborate a little bit on why we are interested in this new mixing method. It's called a phase mixing method. So instead of creating master batches, if you do it the conventional way, because natural rubber and butadiene rubber has different viscosities and different wetting properties, you'll end up with a morphology that your carbon black goes to one phase more than the other. So you have this non-uniform distribution of the filler inside your rubber piece that you made, your molded rubber. So we all know that the amount of filler sort of shows you, it's dictated by the economy of the product, right? The filler is much cheaper than the polymer, so it governs the economics of the compounding, but it's the filler dispersion that controls the quality of the end product made from that compound. So in order to get the beneficial influence of that filler, you would want to make sure that carbon black is sufficiently dispersed. And yesterday, Alina talked about how it's important to make sure that your filler is uh, fully dispersed and how it can be shown like by various tests on RPA if you have a good dispersion or not. Uh, Now, when you do phase mixing, instead of making master batches, you are gonna, it's a liquid phase process that is carried out before the rubber is made into a solid. Uh, so the way you would go about it is that you will create a slurry that contains the filler, and then you will mix that with the rubber in the liquid states, and that ensures you that you get a better dispersion. And then you would do this separately for the two types of the rubber that you're using to make sure that the filler is perfectly distributed in either of those, and then you will mix and then you will dry the rubber and cure it. So that's how it's done. Now, when we look at what we did in this case is that for Comho and Cyber Rosland samples, we made two samples that were done the traditional way, and then another one that was done by phase mixing. So now we are comparing the effect of mixing only. So on the top, you can see that the temperature rise in the phase mix samples is faster compared to the regular samples. And in the bottom, you are looking at the mean deflection. You can see that in the beginning, you are looking at the mean deflection. You can see that in the beginning, they were squeezed down more. But as you look at the final mean strain, mean stiffness, sorry, uh, they exhibit a higher mean stiffness in the end compared to the conventional samples. So you can see that there's a cross section at around 20 to 30 degrees, and after that, your phase mixing samples are doing better. In terms of temperature, the temperature of the rubber piece, the phase mix rubber piece, stays higher all the way, but it won't blow out. While the regular samples blew out at around 35 minutes for Comho formulation, and for Cyber Rosland, they failed between 45 to 50 minutes. So it seems that better distribution of the filler due to better mixing method is creating a stronger filler network. And that is why when you are exerting that strain, you are getting more energy trapped inside your sample. So you get a higher temperature rise. But since it is stronger, the remaining stiffness, remaining main stiffness after you go during duration of the test is going to be higher compared to your traditional mixing methods. So let's switch gears now and discuss another type of test. We are going to talk a little bit about the failure regimes of the material and talk about fatigue testing. So normally you are looking at a static test. This is something that we are all familiar with. You pull a sample. So if you pull to a certain amount before you go through your yield strength, your material can fully recover. So the moment you take off that load, it's going to go back to where it was, and you will recover all that energy. So after you go to the yield point, a passive point, there's always going to be some permanent deformation. And that energy that you gave to your material, some of it is absorbed and dissipated, creating that permanent deformation, and some of it is dissipated in form of heat, and a portion of it is recovered. So we call that first section an elastic regime or elastic behavior, and then The second part where post yield, we call it viscose behavior or plastic deformation, not viscose, plastic, if you're talking about solids here. Um, and then you have material that it's storing some of the energy and it's dissipating some of it. And then you pull further and further until you get to your ultimate tensile strength, after which your sample is going to be broken. Right? Now, if we, instead of this quasi-static or something monotonic testing, so a ramp that is like really slow, we do a cyclic or fluctuating loading on the sample. At first, people thought that your sample is not going to break if you are in the elastic regime. And then in the 1800s, late 1800s, there was an incident where people were looking at a train which had an accident, and the wheels were not experiencing the stresses above yield, but somehow the the wheel failed. So there was an engineer assigned to investigate, and his name is August Wohler, and he's the guy who created the graph on the right. So how is this related to the graph on the left? So we have three regions on the graph on the right. So first, say we are only we are applying a very high load, right? Something similar to your ultimate tensile stress. You you pull once, your sample breaks, and that's done. Now, if you reduce that load to something between ultimate tensile strength and yielded strength, you can probably bounce up and down and change the load for a few cycles, but your sample is going to break really quick. When we go lower than yielded strengths, then it takes longer and longer for your sample to break. So you can have more cycles, right? So as you reduce the amplitude of that oscillating load, the number of cycles that your sample can withstand becomes longer and longer. So that's what gives us this line here, which we call a Wohler line. And there is going to be some value that is called a failure strength, that below which your sample can survive all the cycles that you're applying to it. So we know that it's going to break at some point in the future, and we are going to show it with a dot and an arrow next to it on the graph, meaning that we know that at some time in future it's going to be broken, but it wasn't in the duration of our experiment. So again, so we are looking at various stress levels on y-axis and number of cycles that it takes to break that samples on the x-axis. So we call it an SN curve. So stress versus number of cycles. And we will have three regions in this graph. So the first region is going to be low cycle fatigue. So people say somewhere around 10,000 to 100,000 cycles before your material breaks. That's low cycle fatigue. And then if it takes longer than that, we call it a high cycle fatigue. And then there's the endurance limit below which your sample is not going to break at all. So some materials show that, some materials don't. And now that we have set that backdrop, I'm going to talk a little bit more about what you can do with it on your rubber samples. So when you do fatigue testing, there are three ways of doing that. So you can look at fatigue strength, which is basically you're trying to measure that stress level that, say, you want your part to survive 10 million cycles. So you create that graph, you draw a vertical line and see where it intersects that graph, and then that read the value on the y-axis that gives you the fatigue strength. So you know that your stress level should be below that for the material to survive for a million cycles. Or you can do fatigue life. So here you are looking at a certain certain number of certain stress, and then you read how many cycles it will survive, or you're gonna try to measure that plateau that we had. So you're measuring that fatigue limit, the stress level below which the failure won't occur. So here's an example on a multi-specimen fatigue tester intention. We had two different rubber formulations, and we wanted to evaluate the longevity of that product near the bead of the tire. So these are tension dog bone samples, really small, so 2 millimeter by 3 millimeter by 10 millimeter long. And the test wasn't exactly sinusoidal. So the graph that you see on the upper right is showing you the waveform that was applied to these samples. So it's sort of a pulse waveform that is replicating the rolling tire movement on a certain type of road. I believe it was cobblestone here. And it was done at 70 degrees C, and that frequency was calculated based on the speed of a car on a typical European road. And we tested these samples with an electroforce 3330. It can apply 3000 newtons, and then that load is distributed between 6 stations with a 6 specimen star-like fixture that is mounted on it. So all of these samples are experiencing the same displacement, but you have load cells above each sample. So the moment the sample breaks, there is no resistance. So you will see a drop in load. So load measurements help you find the point of failure as you are applying this waveform to your samples. So here is a picture of the inside of the oven. We remove the oven door to get a better picture. So you can see 3 of the stations and 3 of the arms in this picture. And on the left, there is a zoom in that shows you the samples mounted on the tensile grips. Now, Tim is going to show you another video here that shows how that pulse stress was applied to the sample. Thank you, Tim. And then after we did that, we are going to create an SN curve for these two formulations. So unfortunately, we can only show you a representative graph here to discuss because the information was proprietary and we were not allowed to share. But this graph is very similar to data. So each of those stars on the graph is a test point, right? So we have 6 samples here. So for each run, we are getting 6 points. And then you would average those points to create a mean value and then fit that line that you see there. So there will be 2 lines, 1 line per compound. And this way, because you're testing 6 samples at a time, by doing 4 test series, you're actually getting 24 failures in 1 month. So that saves you a lot of time. Because remember, these fatigue tests are usually really long because you don't design a part that is going to break soon, right? Now, after we do the curve fitting, you're going to get an exponential line that is fit to both. And by comparing those exponential lines, you can compare your materials to each other. So say we're comparing 2 stress levels here, compound A and compound B. So you would draw a horizontal line, then you will look at the intersection with the fit that you did, and then you will come all the way down, read the number of cycles on the x-axis. So you can see here that compound B, the newer trial was actually worse than what they had before. So here is another example. Uh, Here we are looking at filler content in tire rubber. This was a natural rubber. The study was done again on DMA 3200 here with a different type of oven. This is a smaller oven. And here we are looking at two natural rubber compounds. One had 40 parts per 100 rubbers of carbon black, and the other had 60 parts per 100 rubber of carbon black. Uh, Here's a strain sweep. We are trying to look at the pain effect here. You can see that there is a significant drop in modulus for both of the samples. Uh, when you get these rubber samples, it's sometimes not very easy to cut them to a smaller sizes. And because they are stiff, you may not be able to do it on a conventional DMA. So in this case, here it was a good example where we had to go with a DMA 3200 because of that. Looking at the data here, you can see that there is a zoom in of the graph that we saw before. You can see that in the high filler content material, we started with a higher modulus, but as we went to higher strains, its drop was more compared to low filler content. So we start at 2.5 times more modulus, but when we increase the strain to uh, above 10%, you see that the difference is almost halved here. And probably that's an indication here that the flare distribution inside the uh, highly filled sample wasn't really well, so that filler network isn't really strong. As you apply higher strain, the network breaks down, and you don't get as much improvement as you would expect from this sample. Going to the next graph, same two samples. Now we are trying to compare the wet traction and rolling resistance. So now we are doing a temperature sweep like we discussed and looking at tan delta values at 0 degrees C and at 60 degrees. You can see that the glass transition for both of those are similar. So glass transition temperature is minus 44 C. And that is because your TG does not change by addition of the filler. It's an attribute of your polymer and it's going to stay the same. But when you look at tan delta, you can see that increasing the filler content is changing your tan delta. And you are getting a higher tan delta value both at 0C and at 60C. So you are improving your red traction, but at the same time, you are adversely affecting your rolling resistance. Another example of a test that you can do with a DMA on your rubbers is a time temperature superposition. So this is a really powerful technique because it allows you to expand or because it allows you to expand or extend the data that you are generating over a certain range of frequency to much lower or much higher frequencies. Uh, the principle that it is based on is that there is an equivalency between temperature and frequency domains in polymers. So you can predict high frequency behavior by doing cryogenic testing at lower temperatures and also predict low frequency behavior by doing tests at high temperature. So you're sweeping at you're doing temperature steps at various frequencies. You get a lot of data points, and then you are shifting these along x-axis. So our Trio software helps you do that. And then you create, so when you move these are like pieces of a bigger curve of what we call a master curve. And that master curve is going to be over a much larger frequency space than what you tested. So you were testing from 0.1 hertz to 100 hertz here, and you are getting almost 4 times more than that, going as high as 10 to 12 hertz in frequency. Uh, Here, the arrows at the bottom of the graph shows you what was the actual measurement frequency. Compare that to what we predicted based on this principle. So here's the master curve generated on that. So we removed the actual data to show you a better graph. You can compare the width of the frequency range to the overall data that we were able to generate. So if you look at this graph, it is very similar to a temperature sweeps, and that's the basis for time temperature sweep superposition. So it's just like a mirror image of what you would get if you did a temperature sweep on these samples. Going to the next study. So switching gears here a little bit, we are looking at exposure again. So this slide shows you a high pressure TGA 750 model. This is a good test when you are trying to look at the decomposition under very aggressive conditions such as high pressure or corrosive atmospheres. And it allows you to have 3 types of gases, up to 3 types, including CO2 or methane, and then look at your sample behavior as it is exposed to those. So this case study was done on one of our own spare parts. So this was an O-ring, an FKM O-ring that is used in our Rubotherm product line. And this is something that you can do actually. We are looking at how long does it take for the O-ring to break or decompose at different atmosphere and various pressure levels to have a recommendation for replacement of that part. So we did this test at 3 different pressure levels and 2 different atmospheres. So 1 bar, 40 bars, and 80 bar under argon or in neutral environments, and then under air as an oxidizing environment. So here's the graph under argon. You can see, so the way you would go about this is that you would look at the drops. So what are the temperatures at which you start to degrade your sample? And then you would also look at that area that is shown in that dashed circle in the end. So how much was your residual weight? So you can see that there are 2 bigger steps, 2 bigger drops. And then there is a less pronounced drop in the middle. So three steps, one at around 500 hertz, 500 degrees, and then 2 more at around 600 C and 800 C. As we are increasing the pressure, you can see that temperatures for both of those decompositions shifted to lower temperatures. So it means that now your O-ring is gonna decompose at a lower temperature because the pressure is increasing the activity of the gas, and that's also increasing the load on your O-ring. But between 40 bars and 80 bars, there isn't that much of a difference. A better way of looking at it, and maybe it would be easier to understand that way, in trios you can look, so the blue line is just the normal graph, so it's showing you the weight with time. In trios you can look at the derivative of a variable. So now we are plotting the derivative of that weight to show weight change with time. And now it's easier to see those 3 points. So you get 2 very sharp peaks at 540 C and 811 C, and a smaller one at 654. Basically showing you the same data in another way. Uh, Going to the next plot here, now we are doing the same test, increasing pressure levels in air and looking at our sample behavior. In air, we observe the same trend. Age, again, similar decomposition, so significant increase in temperature when you decrease in temperature when you go from 1 bar to 40 bar and 80 bar. But between 40 bars and 80 bars, there isn't as big of a difference. The decomposition in air is more complex, so you can see that in that intermediate range, there are some stuff going on. The graph does not look doesn't show a peak. It's almost gradual there. And what is interesting is that in the end, the 40 bar and 80 bar tests gave you a bigger residual mass. Now we are going to compare argon and air to each other. So you can see here that the decomposition is in air is faster, so the drops are more steep, and it also starts at a lower temperature. So it seems that air is a more aggressive environment as we expected, but and the similar trends were observed for pressure for both of these. So in both samples, when we are increasing pressure, we are shifting those temperatures to lower temperature. The decomposition starts sooner. But in the end, the residual weight under argon was more than what you saw in. So that's the kind of information that you can expect from a typical high pressure TGA test. Another instrument that you can use to understand your material better is an optical dilatometry. So optical dilatometry is using a shadowed light method. So there is a gallium nitride LED light source that is emitting a light on your sample. So this is a contactless method. You can see in the top view of the chamber in the middle there that those green beams are representative of the light that is applied to your sample, and then you're looking with a CCD at the shadow that your sample creates with the increase in temperature. So this allows you to have a lot of flexibility because the sample is not mounted on grips, and it's a good method when you're looking at thin films, irregular shapes, or soft materials. Say you're looking at an LSR, and it allows you to measure the coefficient of thermal expansion or even glass transition. Or with a different variant of this same machine, you can even have 2D measurements of the expansion or contraction of your sample. So an example here is on a rubber sample. The sample, as you can see in the picture, is 10 millimeters by 5 millimeters by 2 millimeters. This is a tire rubber compound. You're increasing the temperature and looking at the onset of that transition, which shows you the TG, and the slope of that length dimension change with temperature is showing us the thermal expansion. Second example, this is a really good example. So in this study, we were not supposed to pick up the sample by tweezer. So the customer really wanted a contact-free measurement. So they even shipped us the sample, and that backing or support material that you can see, it was a really soft and a sticky silicone. And we mounted it on the optical dilatometer. We looked at the dimensional changes with time, and the slope of that curve gave us the coefficient of thermal expansion. So we discussed several methods today, and because we were limited in time, we didn't go in details about some of the other methods. But just to briefly mention them, you can also look at the thermal conductivity of your material. For example, in the heat buildup test, when we were talking about how that heat is trapped inside that rubber cylinder, a part of it could be because that adding different types of fillers and achieving different dispersions is also changing the thermal conductivity. So that's something interesting to look at. Or another example could be the tribological performance of your samples. On all of our rheometers, you can now have a tribometry accessory that allows you to look at the lubrication, the wear and friction between two parts that are in relative motion to each other. A good other test that you can do is a dielectric measurement system. So this is looking at how electrical energy is dissipated or transferred through your material. So you're looking at capacitance and conductance changes inside your material as you are applying mechanical deformation inside a rheometer to it. This is a more sensitive technique than DMA, so it's perfect for studying the effect of fillers that you have added to your material and how the filler network interacts and changes as you're applying mechanical deformation to it. We all know that carbon black is conductive, so as you're increasing carbon black content or you're adding certain additives there or you're replacing it with silica precipitate, how does that affect your final product performance? And for example, could be thermomechanical analysis or TMA, where you can measure the sample shrinkage. It has a wide array of probes, and there are several documents in these available by clicking on that folder icon on the lower right if you're interested. And with that, I would like to finish my presentation and open the floor to take questions. Thank you all for taking the time to be with us today.
Thanks, Adeg. Nice work. I appreciate all that information. We have a high number of questions. We've run a little bit long, so I will pick just a few of them, and then I'll relay those to you, and you can answer them via email. So first question, actually there's a few of them on the flexometer test or the heat buildup test. Just in general, maybe just revisit the difference between the Goodrich flexometer and heat buildup, if any, and then the three temperatures, just repeat those three temperatures that you typically run that test at.
That's a very good question. So the main improvement of testing in an electroforce instrument compared to a traditional one is that you can monitor your viscoelastic data and how they change with time in a heat buildup. So at any given point, you can measure your modulus and your tan delta. And also, you can have perfect monitoring of load and displacement and stiffness with time, looking at your hysteresis data and how they change. So that's one. The test is usually done at 3 different temperatures. So room temperature, 50 C and 100 C, and that is controlled by how you set your oven temperature. And one last point is that, so the standard says either do it for a certain time. So in this case, we tested all these samples until blowout or until 1 hour. Or another way of doing it is that you would continue testing after you reach your maximum temperature for another 25 minutes. And then you'll end the test there. If you are doing a high temperature test, it's recommended to have your samples at that temperature for at least 2 hours before you start testing.
So they reach equilibrium first. Okay, a couple questions on TGA. Just maybe talk a little bit about the atmospheric options, and I think specifically, can you blend gases in the high
Yes,
pressure
there
TGA?
are actually two models of that instrument. That's a very good question. So you have a HPTGA 75. That model only has a one gas flow controller, but on 750, which is a more advanced version of that, you have three reaction gas connections and three independent mass flow controllers. So it allows you to create a blend of your own with those three gases. Uh, so that's an option that is available to you there.
Okay. Shifting gears to the dilatometry question, you mentioned TMA at the end and dilatometry before that. Can you just talk a little bit about the difference? They seem related, maybe where one is better than the other.
A very good question. So these two instruments started in two different industries. So dilatometry comes from metals and ceramics, and TMA is more familiar with polymer audience. But they are basically doing the same thing uh, in two different ways. In this case, we had an optical dilatometer. There is another version that is a push rod dilatometer. Uh, the main difference between what we presented today and a TMA is that here you don't have any contact. You can do contactless measurements. Sometimes you don't want to apply any load on your sample, right? So uh, that's the added benefit of an optical dilatometer here. And also with that different variant that I mentioned with a heated microscope, it will have a lower resolution, but you can look at shrinkage and expansion in 2 dimensions at the same time. The temperature performance on that option would be room temperature and up. But in this one, we can also go through TG and look at the thermal expansion. But anyways, in the TMA, you have a wide array of grips, and you can apply different forms of deformation to your sample and measure your softening point, TG, and thermal expansion coefficient. Also, very important distinction is that you have the modulated option on our TMA now. So that allows you to separate reversible and irreversible phenomena that is going on together inside your sample. Uh, so here, if you were to do the same test on a dilatometer, you have to do a run and then cool it down again and do another run. But in a TMA, you do one modulated TMA, and in that one run, you can say, you can look at the effects of, say, for example, stress relaxation of the residual strain that was inside your sample. So that will be separated from something that is reversible, like a TG peak. So that's a big benefit of going TG peak. So that's a big benefit of going with a TMA over an optical dilatometer. But again, if you're interested in looking at a sample that should not be under stress, then that's where an optical dilatometer comes into play.
So let's wrap up just with one question. Actually, there was a lot of TTS related questions, so I'll just pick one of them, and you can just comment on that, and then we'll close it up and answer the rest via email. So TTS, can I apply TTS over temperatures that transitions are happening? For example, below and after alpha or beta transitions.
Yes, actually, if you look at that graph, we went through a transition. So the answer is yes. It may be a little tricky to do that because you may not be able to do it without considering how your stiffness changes as you go through that transition. But the good news is on all of our DMAs at TA, we have a built-in algorithm. We call it the force track. So it's intelligently monitoring your stiffness change with time, and it's modifying your mean stress or mean load such that you maintain, say if you are doing this in tension mode, you maintain your tensile mode as you go through transition. Or if you are in compression, you don't lose your contact with the top of your sample as your sample softens.
Okay, perfect. Thank you. Okay, well, we'll wrap it up there. Thank you, Sadek, for your presentation. Thank you for everybody for your attendance. And just a reminder, this, as well as the first two parts that were presented earlier this week by Sarah and Alina, will be available for archives if your colleagues, share them with your colleagues or go back and look at those if you missed them. Okay, well, thank you, everybody, and thanks again, Sadek.